Hello, today we're going to learn how to use OpenCL in Houdini to generate terrains in real time. And this is what we will achieve. So let's jump into Houdini. So here we have where we left off last time. So let me just rearrange these. So if you watched my previous lesson about fractals, you saw how we implemented this fractal in VEX. So we had this, let me dissolve this shape here, and then we wrote this VEX code to create this fractal. So let's look at how this was implemented. So we have a snippet here, and then we have a loop that goes through each octave each octave of the fractal noise and accumulate these, and then it will take the resulting vector and go from the voxel we are generating and use that vector as an offset and grab that value and use that value as the new height value. And this was explained in the previous lesson. And one correction here is that this noise here should be curl x noise 2D, and we were using curl x noise. So remember to use the 2D version here. 2D, okay. And if you have a look at the performance, you can see that we can change the amount of distortion, and it updates quite fast. So it only takes a second or two for each update to take effect. And that's because VEX is quite a fast language, and it is compiled and run on the CPU, but it doesn't run in parallel and it doesn't use the GPU. So we can make this a lot faster. So that's what we are going to do today. So let's look at that setup. So let me first of all show the difference in performance. So here we have the amount of distortion again. So if I move here, you can see it is completely in real time and much faster than the other version. And you can also modify other parameters like the number of octaves or the frequency, for example, like this. Okay, so let me explain how this works. So I'm going to disable these, and this is the starting point. And because we are running in parallel, we cannot generate one value based on another value, because that other value might be changed in parallel, because this program runs simultaneously on several voxels at a time to make it really fast. So what we have to do is to read from one place and copy this into another volume. So what I do in this first OpenCL implementation, in this OpenCL node, is to generate again this fractal, but I'm storing this in the mask volume instead of the height volume. And then I will copy the mask back to the height. And finally I will clear the mask. So this will give us the same result as we had before. Or slightly. The parameters are a little bit different, but it's the same implementation. Okay, so let's learn how to make one of these. So I'm going to delete the clear mask, and we are going to implement that together. So let's press tab and type OpenCL, and then let's put this in between here, and let's call this clear mask. And then press P to edit the parameters, and for the kernel name I'm going to type $OS. which will expand to clear mask. And then on the next, okay, we're also going to use a code snippet. So let's click use code snippet so that we can write code directly in the node instead of using a text editor. And then on the second tab, options, we have to run over the first writable volume. And if you are using noise, we have to check this one, but we are not using noise in the clear mask. And then on the third tab, bindings, we have the parameters. So here we can enter mask because we need to be able to modify the mask. And then expand the options and change the parameter type to volume. And this parameter is the mask volume. And because we only have one volume, we don't need to force alignment with other volumes. So unclick this and make it writable but not readable, because we are not going to read from this mask. So now we are ready to implement the actual code. And the easiest way to start is to press generate kernel and just copy this code. Okay, so I have to use the mouse here. Okay. This is quite silly, you can't really. Okay. Copy, okay. And let's paste this code. Let's try again. Press generate kernel and I have to use the mouse for this. And copy, okay, and paste. And we can remove the first lines. These are just for an example. And I'm going to keep this as is, but you might want to clean this up to make it a little bit more readable. And make the names perhaps a bit shorter. Because we have so little space to type here, we don't want this to use up all the space. And you can also put this on one line, like this. Okay, so now we have here all these stride related parameters, and then we have our mask. And I prefer to have no space here. Okay, and then let's just make this shorter as well so we can see what we are doing. So stride X. You don't have to do this if you don't want to, but I'm going to clean it up anyway. So. Okay, stride Z. Okay, so because this is a 2D volume, we don't need the Z part down here. So I'm going to remove this to make it more readable because there's so little space. Okay, so this is the mask volume that we specified here under the bindings. And it comes together with these stride values. And these are used to find out which element in the mask array corresponds to a certain voxel. And the voxel we are working with, I'm just going to rename this. Can be fetched using the getGlobalID. And 0 is the x, y, 1 is the y, and 2 that we just deleted is the z if we use the z. And then we are calculating the index into the mask array by taking this stride offset and this stride x multiplied by x and this stride y multiplied by y. And now we can modify our mask. So let's type mask brackets I. So this is specifying where in the mask is the voxel that we are assigned to work on, because this will run on several voxels at the same time. Okay, so let's set this to 0. And now we have a clear mask function. So let's see, if I disable this, then we have a mask, and if I enable this, then we have the mask cleared. So this code that we just wrote now is working. And the other ones can be set up in the same way. So I'm just going to quickly go through and show how it is done. So this is copying the height field to the mask field, or the height volume to the mask volume. And I call this copy, and then we have to call the kernel with the same name, copy. And then I have these strides again as before, but I have two volumes. I have the height and the mask. And these are defined under bindings. So I have the volume height, which I am writing to, and I have the volume mask, which I am reading from. And the mask has the same dimensions as the height. So you have to click on force alignment. And because this mask is only readable, then we should use a const, global const float for the mask. And the height is being modified. So this is the same as we just did for the clear mask. And I'm setting the height at this index to the mask at this index. And the index specifies which voxel we are using. And let's see if this works. So if I disable this, it will not copy the height from the mask. And let's now look at the most complex one, the fractal implementation. This is the one that actually implements this fractal noise. And again, we have a kernel that I call Fractal, and then we have to use the same name here, Fractal. And I will show the other tabs first. So we have the options, run over first writable volume, and use simplex noise data because I am using noise functions. And if I click this, then I have to put this first. So global const void pointer the x noise. And finally, under bindings, I have the height volume that I am reading. And I want to know the voxel resolution, so I am clicking this, which will allow me to use these resolution X, resolution Y, and resolution Z parameters. And then I have the mask that I'm writing to. And I'm forcing this to have the same dimension as the height. And then I have some extra parameters for the octaves that we just looked at before. That is an integer, and the amount that is a float, and the frequency, which is also a float. And you can see how fast this is. You get the terrain generated literally in real time. And these parameters can then be used here. So the integer octaves, the float amount, and the float frequency. And if you don't know how to write this part, again, you can use this generate kernel, and it will generate one version for you that you can use. Okay, and then the code here is again get x from global ID 0, get y from global ID 1, and then the index using this same formula. So in this case, the destination index, where I will write the height, which I am writing down here, mask destination index. And then I am sampling a source height from somewhere else in the same way as in the VEX version in the previous lesson. So I have this for loop where it goes through each octaves, and the number of octaves is taken from the octaves parameter, and the amount and frequency are also assigned here. And this is the same formula as the VEX version. And we have the curl noise. In this case, it's called curl x noise 2. And then we have to take this dx noise parameter from here. And this is a special OpenCL way to use noise. And then the position in the same way as the VEX version from the last lesson. And then I'm offsetting the position using the noise to find where we are going to sample. And then this is also quite important. So let me go up to the bindings and let's set the octaves to 1. So we have 1 octave here. And let's go back here, and if I am only sampling a voxel in a straightforward way, then you can see we get the aliasing artifacts, because this will take even voxels. You can literally see the voxels it is sampling. So what we have to do here is to use bilinear sampling. And if I do that, so let me switch to the other implementation. So this asterisk slash are used for comments. So I can comment out that code and use this code here. And now you can see everything is smooth. And that is because I am using bilinear interpolation to sample the source. And to use this, we have to include the interpolate h. And to use the curl noise, we have to include the x noise h. Okay, and otherwise it's the same more or less as the VEX implementation. So to summarize, you can see this is really a lot more complicated than using VEX and not at all artist friendly, but it is extremely fast. So if you really need it to be faster, then it is worth the time to make an OpenCL version instead. But otherwise, I recommend to stick to VEX code. So again, this is the final result. So I hope this was not too much to digest and was helpful for you. So see you next time. Over and out.